So I want to talk about how to use Elasticsearch to explore your data to see what you got, and I'll walk through the features of Elasticsearch that might help you. So first, a quick question: who knows what Elasticsearch is? Okay, who actually uses Elasticsearch in production? Okay, very nice, very nice. So I'll make most of you know, so I'll make the introductions very brief, and we'll move on to some more interesting features that hopefully not all of you know, because otherwise I'm just wasting your time. So this is the obligatory buzzword slide. Like, this is all the buzzwords that we can do with Elasticsearch. It's open source. It's based on HTTP and REST. It talks JSON. It's built on top of Lucene. It's scalable, and everything that must be in every talk. But how do you actually use it? So this is how you start. You download it, you extract the tarball, you run it, you're done. You can start using it right away. If you do this step multiple times, you will actually have multiple nodes running on the same machine, automatically forming a cluster. So very simple to start, very simple to experiment. The barrier to entry is very low. You just need to have Java installed. We recommend always the newest 1.7 JVM. So once you have it running, what you can actually do? The first thing, you put data in, you get data out, you can delete data, you can update data. You can basically treat it a little bit as a document store. You just put in any JSON, it will automatically try to detect the data types for the individual fields and do the right thing. That's going to be a repetitive motive that we always try to do the right thing by default. So if you don't really care, you can just leave it and it will do the right thing. If you care, we provide you all the options and encourage you to actually do what you want. If you have some knowledge that Elasticsearch doesn't, for example, some business knowledge, some knowledge about your data, you can always leverage that. So that's the simple part. Now, what else would you expect from a product that's called Elasticsearch? I'm guessing a simple search. So the simplest possible way how to do a search is you just do a curl, you put a query parameter, and you put in the word, the phrase that you're looking for. In this case, we're just looking for a meetup. Which would translate roughly to this query. I just added a little more to demonstrate that in this part you can actually use the entire power of Lucene query expressions. So you can just limit the search to some field, you can do Boolean operations, and many other things. You can do even ranges, you can do inequality operators and everything. But this is something that's not very convenient, like paste together a string and run it. It's not very good. So instead, what you would typically see in production is queries like this. So this is a filtered query. There's a filter and a query. The difference is filters are super fast. They are cached. So if you use individual filters in more than one query, you will get a very significant performance boost. Even if the filter is just part of a more complex filter, it will still be its cache will still be reused, and it doesn't contribute to the score. Whereas queries also limit the result set, but also give you the information how well a document matches. Not just whether it matches or not, but how well. So for example, we use this because we are even here saying that title is more important for us than the body. So if there is a document which has Python in the title, it will be more relevant to our search. And of course, we can do Boolean logic, so we can always exclude PHP. It's always good fun to exclude PHP. So this is a pretty simple query in the DSL. You see that it's all just JSON, all just HTTP. We're talking to an index called stack. We're just calling the search endpoint. Nothing groundbreaking here. But it gets more interesting. So as I said, because filters are cached and they're much more performant because of that, you should always use filters. Only use queries if you care about the score and if you have no other choice. It will help your performance a lot. And now comes the interesting part, both logistically and so we'll actually, I showed you some queries. Now we'll try to see how it actually works. So the first demo is with search. So this is a similar query that we saw. I just, for the benefit of the conference, I just edited RuPy so that all the RuPy people here wouldn't feel left out. And so if we execute this query, what will happen? It took 18 milliseconds. It's just running locally. It succeeded in all the shards. We'll see later how an index is divided into shards, and that's the way how we do scalability. We totally hit 800 documents almost, max score, and here we have the individual results. If you actually want to see them, it's not going to be pretty. It's a lot of data. So instead, just so that we don't have to see the entire blob, we can just always limit the results field. So if I actually here at the end of the query just limit the fields, I can make the results more readable. So I only care about the creation date and the title. So far, perfectly simple, just searching, limiting fields. Everybody can do that in their sleep. Now comes the more interesting part, because we've limited the fields only for title and creation date, but we are also searching from through the body. But we don't want to get the entire body back. We only care about the individual relevant parts. So we just tell ElasticSearch to highlight the relevant parts and to give us a fragment of size 50 for each match in the title and in the body. So how this looks is, for each hit, we get a list of fragments, and in those fragments, we have highlighted by default with HTML markers the individual matches. So notice that we are searching for Python in lowercase, but it will be matched even with a Python in uppercase. If we had some information in Elasticsearch about synonyms, and for example, if we had a synonym that Python is the synonym of awesome, and we would search for awesome, we would still get this highlight that would highlight the word Python, even though it's nowhere near our query. So just using the power of full text for good in the world and world peace. So what else can we do? I'm just blowing through this because most of you know Elasticsearch, so this is just very simple queries. And here I'm just complicating things a little bit. I'm adding a must and must not branches. This is something that we already saw on the slide, so I'll just blaze through this. If I'm moving too quick, just raise your hand or something. The chances are that you're not the only one who might lost behind. So again, everything still works. I still get the highlights and the fields. And notice that I'm working with the same query. I'm just adding more and more things into it, and this is a very natural process that you can use in development. You start with a simple thing, and you refine your query, add filters and queries to get everything you want. Now let's finally do something interesting. This is again a query, and right now I added a hasChild query. hasChild refers to one of the types of relationships you can actually store in Elasticsearch. You can have a parent-child relationship. For example, this data, that's data from Stack Overflow. Because all the data are public, I just always use it when I need to show something off. So we have the answers and the questions loaded, and we told Elasticsearch that the answer is always related to a question. So here I'm actually searching for questions, but I added a query that runs on the answer. So for those of you who haven't caught on a little bit, we just performed a join in the NoSQL database. And it just works. It works in a distributed manner. It works very, very efficiently. And it allows us to use any sort of query here for the related object. So we are searching through answers, but we are getting back questions based on the relationship that we have defined earlier. Just to make sure that it works, that I'm not lying to you much. We see that we still get some results back, and it actually matches the search criteria. So here we are searching for questions where somebody asked about PHP and didn't even mention Python or Ruby, and he got a response with Python or Ruby in it. So basically just some poor soul looking for help with PHP and just some smart ass telling them like, just switch to Python. Yep, a question?
In the query, if you scroll up, there's an element in the dot part. There's an element that says shards.
Yes.
Am I jumping ahead?
A little bit.
Sorry?
We'll get there, maybe. Another question? Yes, you can always have one parent. That's a limitation. It's a parent-child. But data doesn't have gender, so. And one last thing that we'll add is some sort of aggregation. So we can not only retrieve individual records, but we can run some sort of aggregation. So here I'm asking for tags and frequency. Tags is a terms facet, so it will take all the possible values of the tags field and return me count how many documents in the results that actually have that value of the field. And the second one is a date histogram, which I've just given it. I've just given it a field with the date time in it and an interval, and it will actually say me for each month, according to this field, how many documents matches. Now I can run this and show you the results, but it's, once I scroll down, but it's not very readable in Vim. And that's why we are going to Kibana. So Kibana is a front end for Elasticsearch. It was originally developed to work with Logstash, and it's a JavaScript thing. So everything you see has been actually computed server side inside Elasticsearch. This just uses the Elasticsearch API, and this shows you what Elasticsearch can do and how quickly. This is the entire data set from Programmer Stack Exchange. You can see that it reacts pretty snappily to any query that I make, and we can see the date histogram here, even split for 3 queries. We have split the data set by number of comments that each of the document has. You can see the distribution by tags. You can see the total amount of documents with 0 to 2, 2 to 4, and 4 and more comments. And you can even see if we scroll down, you can see the individual results with all the fields. You can even see their JSON source, but the table is generally more useful. So this is something that comes out of the box with Elasticsearch. You just install it as a plugin. It's just a bunch of JavaScript files, and it enables you to get a nice interface for the faceting. Sure.
What's the name again?
Kibana. The name is Kibana. It's not anywhere here. It's K-I-B-A-N-A. And okay, so that was searching. This is, if we had more time, this is the query that we would have constructed in all the steps. You can see that you don't have to write SQL to be able to run unintelligible queries that nobody will understand. This is some additional things that we didn't go through because I want to show you something more interesting. So the first interesting thing is a percolator. what Percolator is a reversed search. So I will index queries, and then I'll run documents, and it will give me back the queries that matches. So if you have any sort of custom alerts for your users, this is exactly what you need. First, we create an index. That's not interesting. And here we run a simple query. Again, the Ruby and Python, and we get no results back because we have just created this index. But what if we want to monitor? What if we want to create an alert for when a new document comes in that matches this query, so we could get an alert? Sure, we could keep running this query, but that's sort of not very good. So what we can do instead is there is a special index that's called _percolator, and then we just insert the query. We associate any metadata with it. For example, this is the user who has created this query. And then whenever we see a new doc, we can just send it in. And wait, I just need to run this first, so it will actually get indexed. And now whenever we see a document, we'll just send it to be percolated, and we can see that it matched the RuPy query, because in the previous one, you can see that we named the query RuPy here. That's the ID of the document. So just like this, we get an alerting system. It can scale to millions of stored queries that we can run percolations on, and every time we see a document, we can just send it in and run the percolation queries. The metadata is there also so that we can actually filter and only run it against some of the queries that we have stored. For example, here let's run only the queries that were stored by the user Zeiste. So still the Ruby is there. So very powerful feature if you have any sort of alerting system, if you want to, or for example, if you do dynamic categorization. For example, you have user-defined categories, and you want to see which category this document belongs to. Usually it's very hard because user-defined categories, it's easy to do the search and get the objects that belong to the categories. But if you have the object and you want to see where it would belong, that's a harder problem. But it's solved for free using the percolator. So moving on very quickly, Autocomplete. I will not demo this because we're running out of time, and but it basically just does an autocomplete. It bypasses the index entirely, so it's incredibly fast. It's so fast that if we get a response that's over 2 or 3 milliseconds, we consider it a bug, and we can definitely do that. How it works is you basically index some document. You say all the possible variants of what to autocomplete on. You can associate some payload with it and some score, and then when you just run a suggester, even on a single letter, you will get back results very fast, and it enables you many times to even skip the search phase. If the user can find what they want just by autocompletion, you don't have to search. So it's very easy on resources because you don't run the full search, you just run the autocomplete. That's very fast, and it's excellent user experience because the users get back results literally as they type. Because when you get back a result within 2 milliseconds, not many people can do more than 1 keystroke in 2 milliseconds. So you can literally just complete as they type. And the last feature I want to mention is a suggester, as in, did you mean? When you type something into Google and you misspell something, or even though it might be spelled right in a different context, it will tell you, did you really mean this instead of what you typed? And this is better explained on an example again. So let's index some data. So the data is yellow pages. So we have three people. We have Johnny Mnemonic, Johnny Cash, and Johnny Walker. And it's all Johnnies, but they're spelled a little differently. So when we do a search for Johnny Walker and we don't really know how it's spelled, we don't get any hits back. And that's not necessarily a fault of the user because he just heard the name Johnny Walker and he doesn't know how it's spelled. So if we just add a suggest phase to it, so we have the same query, but we also added a suggest. So I want to suggest on the text Johnny Walker, and I have some magic attributes here that will basically tell me where to get the suggestions from. And I run this, I still get no results, but I get the suggestions, and it tells me that, did you really mean Johnny Walker? So you see that even when a word is spelled correctly, we can identify based on context that it should have been spelled differently. And for clarity, we can always just highlight what we have changed. So we can tell the user what they meant probably, and show them where the difference is. Again, this is very fast. It's associated with a query with very minimal cost, and it's a very nice feature that's otherwise very difficult to do with any other tools. Your typical relational database will not give you this functionality. Okay, so just last question. We'll just answer the question whether it's web scale. Yes. Now we would talk about the shards and everything, but we've run out of time. So if you're interested in the scaling aspect, just come talk to me anytime. This is how it would look if I were to talk about it, but I'm not. So just thank you, and if you have any questions, you have to answer them.
So just first of all, thanks for the talk, it was great. And also there's around like 8 minutes left, so there's gonna be either a lot of questions or you can still talk about
Okay, let's see how
shards.
many questions we have, and if we don't have enough questions, we can do the sharding and scaling. So there.
So I have like 5 questions, but maybe
Yeah, we're not going to do the demo, sorry guys.
I'm very interested in the functional. First thing is, can you use it as a NoSQL database, or is it more like a search engine?
So the first question was if you can use it as a NoSQL database. Sure, you put data in, the data is there, you can get them out. If you mean that, then absolutely.
All right. And the second question is, because I've used a few Lucene-based solutions in the past, and they tend to have common problem when you are adding or updating documents and you're searching at the same time. Sometimes the solver has those problems of performance in that case. Did you guys solve that? Or is
So the question is that many Lucene-based solutions have a performance problem when you're indexing and searching on the same time. How we do this is if you index a document, there is a grace period when the document isn't available for search. You can request for it to be available immediately, but that's rather expensive operations. Instead, what we opt for is we run a process in the background that creates the Lucene indices. So we solved it that way. We've seen throughput of several gigabytes per second for indexing speeds with certain customers. So there's definitely not that much performance hit when you're indexing. You definitely can fine-tune all of this. You can and you can mix and match based on what your use case is. But we have seen very high throughput for both in and out situations, and we saw no performance problems.
But if I want the document to be available immediately for search, I will have to say performance problem is solved. This will run to the index all the time, and this blocks the queries actually.
It doesn't block the queries. It will create a new Lucene segment, but we're getting way too technical. Let's talk afterwards. And any other question? That's a good question. I don't know. So the question was whether you can use Kibana to query the parent-child relationships. To be honest, I don't know. I'll be happy to find out for you later. My safe answer is Kibana is only JavaScript. It's open source, and you can create your own panels. So it should be fairly simple to add that if you so desire. There's a
Interested whether it was possible to use a percolator automatically when a document is inserted, and whether you have some sort of complication support when the percolator hits basically.
yeah, so the question was whether you can run Percolator automatically at index time and whether there is some sort of alerting system. So the first is no, we've had this option before, but it wasn't very ideal. So what we would recommend instead is you can do you can index a bunch of documents and then run percolation separately, or you can just post in one bulk request that can do the index and the percolation. So that's the first, and the second, no, we don't do any alerting. We are simply we don't call you. You have to call us with the percolation, but the percolation is synchronous, so you will get the result immediately. It really works real time, even with a huge number of queries. In the new version, 090.5, the percolation is finally distributed, so it scales very well, literally to millions of queries used for percolation. Any other questions? So non-string, what the support is for non-string data types, it all depends on your analyzers, on what value or what structure you get out of the data, and we then search on that. That's a process that's run both for documents and for queries. So for example, theoretically, it is possible to implement, for example, image search. If you had a sophisticated enough analyzer that would extract some information from the image, for example, colors. And then when you do a query with an image, it would do the same process and then it would match it. So that should work. Of course, we work perfectly fine with stuff like geolocation, all different number formats, date logics and everything. That's supported out of the box. For the rest, you would have to do some sort of your own analyzer to get the data that you actually search through. Okay, any other question? Do we still have time to do a short demo, or are we done here?
Like 2 minutes left?
2 minutes? Oh, I can do it in 2 minutes. So what you see here is head, which is a plugin for another plugin for Elasticsearch, and it actually displays the information about my cluster. So I have one node and one index. The index has have 5 shards, which is the default. By default, each index is split into 5 different shards, and there is one replica associated with each shard. The number of shards you cannot change. Once you create an index, it's fixed. The number of replicas you can change at any times. So if I just change the number of replicas to 1, and I do a refresh, and you can see that I've requested each index to have at least 1 replica. So we see that there are some unassigned shards. And we also see that the cluster is now yellow. Yellow means that we didn't lose any data, but not all the requirements that we have for the cluster have been met. For example, in this case, not all the indices have all the replicas that they need. So if I just start another node, now we see that there is another node that started, and it automatically took all the unassigned shards and took them and now the cluster is green because everything has the 1 replica that it needed. If I change it again, that there doesn't have to be a replica, it will just get rid of the replicas, and instead it will distribute the shards with the data across the cluster for more performance. So not a single node is overloaded. So we see the process, how the cluster is rebalancing itself. If I start another node, just by running the ElasticSearch process with the same configuration on the same machine, it will just reform the cluster. Now we see a third node, and again, the cluster is rebalancing itself. And I can just request replicas to be allocated. And you see now we have some unassigned replicas, and they're slowly being allocated at free clusters. We see that the cluster is yellow because there are some unassigned shards. And once everything is finished syncing, it will go green again. And what this means is if I actually kill a node and the node goes away, we didn't lose any data. We lost some replicas, and the cluster went to yellow because the replicas are not allocated, and it now slowly starts to get to the green state again by allocating the replicas. So as long as you didn't lose more nodes than you have the number of replicas, you should always be safe. So this is how we scale. This is how we do high availability and security. The scaling is done by the sharding. You can define the sharding when you create an index, and the security and the high availability is done by setting the number of replicas. And that is indeed all now. So thank you very much.